Okay, so we've got an integral here, and we're going to try and use Cauchys theorem to integrate this function here. So we've got e to the z over 4 minus z cubed with respect to z, and the parameters of integration are the contour gamma. So gamma is defined as the modulus of z equals 2. So let's just quick draw that up on the complex plane. So that's the reals, that's the imaginaries, that's the origin, and z equals 2. So this point here will be 2, this point here will be minus 2, this point here will be plus 2i, and this point here minus 2i. Okay, now this region here, this one gamma, we can see that this is a simple closed contour and it's inside the complex plane. And what we could do, we could put that inside another simply connected region, which would give us a radius or a modulus of 3. Okay, so that's a radius of 3, this region here. So what we can say is that all the points inside gamma are contained in this point here and the complex plane. So there are rules for Cauchys theorem. So Cauchys theorem. So the rules for the Cauchys theorem are now all satisfied. Now next what we've got here is 4 minus z cubed. So what we're interested in now is 4 minus z cubed equals 0. So obviously that's the case when z equals 0. When z equals 4. So when z equals 4, this function here becomes analytic. We can't, it's undefined. But when we're dealing with Cauchys theorem, that's the points that we're interested in. So the z equals 4, that's going to be somewhere out here. That's the point 4. Now as that point 4 is not contained within gamma, what we can say is that the integral across gamma of e to the z over 4 minus z cubed dz equals 0. And that's a very easy way of integrating that function across the contour gamma without actually doing any integration.